Hello dear student, this is Devang Shah from LJ Institute of Engineering and Technology. We have been learning the subject basic electrical engineering, and so far we have been discussing the chapter AC circuits. Now in AC circuits we last time we have discussed about the star 3-phase AC circuit. Again in our 3-phase AC circuit we are going to learn today about the 3-phase delta AC circuit. So if we talk about the our content, that what we have been learning since in this particular part. So we have gone through the introduction of 3-phase AC circuits, then we learn about the 3-phase star connection. Today we are going to learn about the delta connection or 3-phase delta connection, and then power measurement. So if we talk about the 3-phase delta connection, will the common definitions we need to understand on all those definitions, like related with the balanced load, unbalanced load. So in balanced load, all the impedances are connected in a circuit are same, equal, having the same value. Same way unbalanced load, that means all impedances are connected in a network, all are having the different values or not equal, right. Same way is the balanced phase voltage is nothing but all the voltages in a star or in a delta 3-phase AC circuit, all are in a same magnitude but are available at 120 degree apart with each other. Same way for the balanced phase current, where all the current magnitudes are same but are available at a 120 degree apart with each other. So this is a common terminology, definition or words that we need to satisfy to understand the star 3-phase AC circuit or a delta 3-phase AC circuit, right. So we learn about again some of the introduction part, where we have last time discussed the star connection. In our today's session we are going to discuss about the delta connection, where ultimately there is a generation, and this generation is distributed over a load. So it's a complete connection, and that connection we always define or we satisfied with the balanced system. Again, this is a part of introduction, where today's session we are going to learn about the 3-phase delta circuits. So you can see this is the specific shape of delta, where this is only a kind of star shape and delta shape we need to understand. So this is the delta shape, where all these 3 phases you can see, red phase, yellow phase, blue phase are connected here. The starting and ending end of this winding are connected together, and that will define as a mesh shape or the closed loop, right. So this shape we define as a delta shape. So in this particular delta shape you can see here, as I have discussed, there is a absence of neutral line at one of the end of winding is not connected to the common point. That is what we have discussed during the star connection. You can see where there is absence of neutral line, right. So straight away if you talk about the delta connection, where the common important points we need to understand, and those points are like phase voltage, that is defined as a VPH, is nothing but the voltage across each phase is defined as a phase voltage, VPH or EPH. Same as a line voltage is nothing but the voltage difference between two lines is defined as line voltage is called EL or VL. Same way the phase current is nothing but the current flowing through each phase is defined as a phase current, which is nothing but IPH. Same way the line current is nothing but the current flowing through each line, which is defined as a line current, which is a IL, right. So in this particular terminology, if you talk about, and this is the delta connection, where you can see there are 3 phases R, Y and B, and the current are flowing through each phase we define as a IR, IY, IB. Same way line voltages we define as VRY, VYB and VBR, right. Same way here line current we define as IL1, IL2 and IL3, right. So here this is the same terminology. If you look for here, the current flowing through each phase is defined as a phase current, and current flowing through each line is defined as a line current. Same way voltage generation of each phase is defined as a phase voltage, and the voltage difference between two lines we define as a line voltage, right. Now our terminology is same as the, that is what we have discussed during the star connection, where these 3 points we have to discuss. Point number 1, we have to find the relationship of voltage and current. So we have to find the relationship between line current to phase current and line voltage to phase voltage for the delta. Same way point number 2, that we have to draw the phasor diagram, and point number 3, that we have to calculate the power, and that power is nothing but 3 times of power per phase. So one by one if we look for all this voltages and currents, so we discussed, this is the delta connection where you can see there are three phases R, Y, B, there is absence of neutral line. So, you can see here whatever voltage is generated in one phase is same as the voltage difference between two lines. So, we define here R phase is like a line number 1, this is line number 2 and this is line number 3. So, the voltage drop across each line you can consider as VRY, same way VBY and VBR, right. So, here the current passes through each phase we define as IR, IY and IB, which is nothing but ultimately is passing through the line. So, that line current IL1, you can see here IL1 is nothing but the difference of IR and IB, IL2 is nothing but the difference of IY and IR, and IL3 is nothing but the difference of IB and IY. So, from this if we first start and try to understand this 120 degree apart with each other, that phases R, Y and B. So, first I am looking for a balanced delta connection, where in a balanced delta connection if we talk about all those 4 parameters, where one of the parameter is called phase voltage is defined as ER, EY and EB. This is nothing but the voltage across each phase. So, voltage across red phase we define as a ER, voltage across yellow phase we define as a EY, voltage across blue phase we define as a EB. So, overall is in general it is defined as a EPH. Same way, if we talk about the phase current, then IR, IY, IB and IPH. So, in general we define as a IPH. So, here the line voltage if we define as the voltage between two lines or the voltage difference between two lines we define as the VRY. This is nothing but the voltage difference of between phase R to phase Y. So, here we define as VRY, VYB, VBR and in general it is VL. Same way the line currents is IL1, IL2, IL3 and in general it is IL, right. So, if we consider the complete this 3 phase delta system is a balanced system. If it is a balanced system, then the phase voltage is ER is equal to EY is equal to EB is equal to EPH. Same way the phase currents are IR is equal to IY is equal to IB is equal to IPH. Line voltage is VRY is equal to VYB is equal to VBR is equal to VL, and line currents IL1 is equal to IL2 is equal to IL3 is equal to IL, right. So, now with this consideration our next job is to find the relationship of voltage and currents, right. So, first we as this is a mesh or delta connection. So, you can see from the circuit there are 3 phases R, Y, B. So, here the and all are 120 degree apart with each other. So, if I am looking for the voltage VR bar, that is the line voltage between two lines 1 and 2, VRY, VYB, VR is same as the line voltage VL, right. So, all the line voltages are same because the system is completely balanced. So, if now I am looking for the relation of line voltage versus the phase voltage from this 120 degree apart with each other. So, you can be easily find here from this here VRY is equal to ER, VYB is equal to EY and VBR is equal to EB. So, here from this circuit diagram you can straight away say that here the line voltage is same as the phase voltage, right. Now, this is not the case was with the star connection, because in star connection current were same, but here in a delta connection the voltage were same. So, line voltage is same as the phase voltage for a 3 phase delta connection. Now, if you are talking and find the relationship of current, where you can see straight away the current which is passing through line number 1 I consider as IL1, and that IL1 is equal to IR minus IB. So, if we apply here Kirchhoff current law at node R, same way node Y and node B, right. So, once you apply the Kirchhoff current law and you are looking for current IL1, IL2 and IL3. So, you will be able to find like this way: IL1 is equal to IR minus IB, IL2 is equal to IY minus IR and IL3 is equal to IB minus IY, right. So, you can see here now this all these 3 currents are nothing but the subtraction of the vector quantity. So, since it is the vector quantity, so here I am stuck. So, once you are going to stuck, only one master key will help you, and that master key we define as a phasor diagram, right. So, I am going to solve this particular terminology and looking for to find the relationship of line current versus phase current, right. So, by taking the phasor diagram, I am going to solve this particular terminology where I am going to solve all this particular 3 equations IL1, IL2 and IL3. So, first we talk about IL1 is equal to IR minus IB, right. So, the vector of IR here and IB is now in opposite direction, it is minus IB. So, now we have a two vectors IR and minus IB, and between this now I am looking for IL1. So, using the parallelogram method, if you find this diagonal, then using a parallelogram method you will find the magnitude of IL1, and that IL1 is nothing but you can use you can solve using the trigonometry. Same way you can use the parallelogram method and you can find the vectors of IL2 and IL3. So, likewise if you find this, then at the end you can be able to find the IL is equal to 2 multiplied by the phase current magnitude of IR IB cos 60 divided by 2. So, from this you can be able to write this equation IL is equal to 2 times IPH into cos 60 by 2. Once you are going to solve this particular equation, and you will be able to find IL is equal to root 3 times of IPH, right. So, here I can say that for a 3 phase delta network, the line voltage is same as the phase voltage and the line current is root 3 times of the phase current, right. Again I am going to repeat, for a 3 phase delta network, the line voltage is same as the phase voltage and the line current is nothing but the root 3 times of phase current, right. So, using this, if I am going to use in a power calculation, total power is equal to 3 times of power per phase. So, if I am going to use this, then VPH into IPH into cos phi, that is a power per phase, and instead of IPH I am going to write IL by root 3. So, the final equation you can see here, the total power P is equal to 3 multiplied by power per phase. From this you can be able to find 3 into VL into IL divided by root 3 into cos phi, where you have put the value of IPH is equal to IL by root 3, right. Now, from this you can be able to find the total power P is equal to root 3 times of VL IL cos phi, right. Now, here the equation is same by the shape star or delta, but always remember when you find the total value in terms of the 3 phase delta, see the equation is same, but that power is the 3 times of power utilized in a star network, right. So, this is what we have covered here, total 3 points, the relationship of voltage and current, then phasor diagram, and then last is the power calculation, right. Thank you dear students. If you find any question, please write in a comment box. Thank you very much.